We will be solving question 43 of GATE Chemical Engineering paper from 2019, and the question is stream A with specific heat capacity CPA of 2000 joule per kg Kelvin is cooled from 90 to 45 degrees Celsius in a concentric double pipe countercurrent heat exchanger having a heat transfer area of 8 meters square. The cold stream B of specific heat capacity CPB is given as 1000 joule per kg Kelvin. It enters the heat exchanger at a flow rate of 1 kg per second and 40 degrees Celsius. The overall heat transfer coefficient U is given as 250 watt per meter square Kelvin. Assume that the mean driving force is based on the arithmetic mean temperature difference, that is delta T AMTD is given as this formula, where T in and TI out refer to the temperature of the ith stream, where I is equal to A and B at the inlet and exit respectively. The mass flow rate of stream A in kg per second is dash. So for this given double pipe countercurrent heat exchanger, and we have been given this AMTD, so we don't have to use this straight temperature difference or log mean temperature difference. We have to use this arithmetic mean temperature difference as the mean driving force in this question. And the mass flow rate of the A we have to find in kg per second. So let's just draw a schematic in which this is my tube side. This is the shell side. Let's just assume that the A stream enters the tube. Okay, so A enters from here and U is here, and we have been given as counter current heat exchanger. So B will enter from this side and leave from over here. And then we have been given Cp of A as 2000, and it is cooled from 90 degrees Celsius to 45 degrees Celsius. Whereas for the cold stream CPB we have been given as 1000 joule per kg Kelvin, and it enters at 40 degrees Celsius, and mass flow rate we have been given as 1 kg per second from here. So the overall heat transfer coefficient U is 250 watt per meter square Kelvin, and we have been given delta T AMTD. Arithmetic mean temperature difference is given, and the mass flow rate of A is like we have to find. So yes, for the A stream we have this inlet temperature and outlet temperature, whereas for the B stream we only have this inlet temperature. So we also need to find the outlet temperature over here. So let's just call it as T out. So we can write simple energy balance for the hot fluid, cold fluid, and the heat exchange across the heat exchanger. So that we can write it as so for the hot fluid we can write it as m dot h into Cp of h into temperature difference T in minus T out of, let's say, h. Similarly for the cold fluid we can write it as m dot c Cpc Tc in, no, it will be Tc out minus of Tc in, and this will be equal to the heat exchange across the heat exchanger. So let's just, it will be UA. Now we will be using arithmetic mean temperature difference over here. Okay. So now let us just equate the last two terms. So from here we will be getting, from here I think we will be getting the value of this. We should be getting the value of T out. So let's just write it. So the m dot c we have been given as 1 kg per second. 1 into CPC we have been given as 1000 from here, and T out we haven't been provided, and T input is 40. So from this you can write 250 into area we have been provided as 8 meters square, into, now we can find the delta AMTD. So that is equal to TA in plus TA out by 2. So it will be equal to 90 plus 45 by 2 minus TB in is 40 plus T out upon 2. So from here we can write this as 1000 T out minus 40 is equal to 250 into 8 will be 2000. 90 plus 45 by 2 will be equal to 67.5 minus of, let's just keep it as 40 plus T out upon 2. So we can solve this and we will get T out minus 40 is equal to 2 into 67.5 minus 40 plus 2 out, right? So T out will be equal to 40 plus 2 into 67.5 was 135 minus of 40 minus of T out. This term will get cancelled and it will come to T out is equal to 135. So this T out will become 67.5 degrees Celsius. Now again, now we will be using this energy balance between hot and cold fluid to find the required, that is the mass flow rate of A. So let's just write it as T out minus 40 CPC. So from here we can replace the values. So that is mass flow rate was 1 into 1000 into T out minus 40. M dot C we have to find, CPC for the cold fluid. CPC is given as 2000 into temperature is changing from 90 to 45. M dot A will become 1000 into 67.5 minus 40 upon 2000 into 45. So yes, we can solve this and the final answer will become 3055 kg per second. So yes, the mass flow rate of stream A is given by this 0.3055 kg per second. And we have been asked to round up till 2 decimal places, so we can report the final answer as 0.31 kg per second.